Hello guys, this is Prime Concept. Welcome back to my channel. In this video, I want to consider a very important aspect of electromagnetism, which is electromagnetic induction. So we want to see the concept behind this and how this helps to simplify our day-to-day activities, right? By the functions or uses of machines, electric machines and transformers, and even what makes this video possible. So quickly, we want to explain this concept. Now, first, you want to understand that we have two big names when it comes to electromagnetism. There are so many names, of course, but I want to point out two big names and how it connects to electromagnetic induction. First, we have a scientist known as Hans Christian Oersted. Hans Christian Oersted. Hans Christian Oersted, on a particular day, was delivering a lecture to his students. So he was trying to illustrate an experiment using a conductor, a wire. He connected a wire to a battery, and then there was a compass needle very close by. That was unexpected. The compass needle was closed. So he was trying to explain the flow of current right through a conductor when he connected the conductor to a battery. And when that conductor was connected and the circuit was closed, he noticed that the compass needle deflected when immediately he closed the circuit. He removed that and noticed it went back. Then when he closed it again, the compass needle deflected, and the students were amazed. And that was the first time this was observed. So that experiment quickly brought to his notice that whenever you allow current to flow through a conductor, that conductor creates that flowing current creates magnetic field around that conductor. In a simple way, when current flows through a conductor, that conductor begins to behave like a magnet, right? So that when you bring any metal around that conductor, it will be attracted to the conductor. So that experiment was carried out by Hans Christian Oersted. So Christian Oersted actually summarized by his experiment by telling us that electricity actually creates magnetic field. That with electricity you can create magnetic field. That is what he told us. Then he discovered this actually in the year 1820. Then about 11 years later, that was in 1831, another scientist came up, which is Michael Faraday, which you know as a popular scientist. He came up and he asked himself a question. He said, if electricity can create magnetism, then does it not mean that the reverse can also be possible? So he asked himself that question. Why not try the reverse and see if magnetism can also be used to create electricity? And then he led him to carrying out an experiment. So what did Michael Faraday do? Michael Faraday brought a conductor and he made it into a loop. A loop is a closed path. So he brought a conductor and made it into a loop, a closed path, just like you can see, like my hand, a loop. Then he brought a magnet and moved the magnet in and out of that loop. Now he connected that conductor to a galvanometer so that if there is current in that conductor, it will be dictated by the galvanometer. So he noticed that when he moved the magnet in, the galvanometer deflected. When he brought the magnet out, it deflected in the opposite direction. So, and quickly he noticed that a changing magnetic field would induce EMF. So this is the concept and the idea of electromagnetic induction, which was actually founded by Michael Faraday. So I can summarize this by saying that Christian Oersted discovered that electricity can talk to magnetism, or say electricity creates magnetism, and Michael Faraday, on the other hand, realized that magnetism also can create electricity. Now, but there's a special case for Faraday because it's not just all magnetic field that will create this. So there's a special condition, which is why you should stick with me in this video, so that you really learn the idea of Michael Faraday. But these two names are worthy of notes. This first one, and then Michael Faraday. Michael Faraday in 1831. So you should take note of this, his idea and Michael Faraday's idea. Now quickly, let's start by explaining the term electromagnetic induction. Now, what is electromagnetic induction? By definition, electromagnetic induction is a phenomenon whereby EMF is induced in a conductor whenever there is a relative motion between the conductor and a magnetic field. That is electromagnetic induction. So let me write it very quickly. Electromagnetic induction is a phenomenon where EMF is induced in a conductor whenever there is a relative motion between conductor and magnetic field. So this is what we know as electromagnetic induction, that you would always induce EMF whenever there is a relative motion between a magnetic field and the conductor. So it tells you that there must be motion so that EMF would be induced. So this is a broad explanation which incorporates Faraday's law. So that is the next thing we want to explain. So quickly, we're going to look at Faraday's law of electromagnetic induction. Now, Faraday's law is actually divided into two. We know one as first law, Faraday's first law of electromagnetic induction, and second law. So we're going to state that in the original form before the modification. A modification was actually made to Faraday's law, but we're going to state it the way it is first, then introduce the modification and tell us who actually made that modification. So Faraday's law. Faraday's law, first law. The first law says that EMF is induced in a conductor whenever there is a changing magnetic field. That's the first law. EMF is induced in a conductor whenever there is a changing magnetic field. That is to say, that is what I just explained earlier. If I have a conductor and I begin to move a magnet in and out, that conductor would induce EMF. So EMF is induced whenever there is a changing magnetic field, right? Whenever magnetic field moves, or whenever a magnet moves through a conductor, EMF is induced in that conductor, right? Now, if that conductor forms a closed loop, if the conductor forms a closed loop or circuit, current is induced, right? Yes, so if you now have a closed circuit or a closed loop, then that EMF would in turn give rise to current flowing through that circuit. So this is Faraday's first law. It tells us of the possibility of EMF appearing or being induced whenever magnetic field is changing. Then the second law tells us about the magnitude of that EMF that is induced. That is what the second law is about. Second law. So the second law says that the induced EMF, the EMF that is induced, is proportional to the rate of change of magnetic flux linking the circuit. So I'll repeat that. The induced EMF is proportional to the rate of change of magnetic flux. Take note of the fact that it is magnetic flux. Remember, we have magnetic flux and we also have electric flux, but the EMF that is induced is proportional to the rate of change of magnetic flux linking that circuit. So the EMF induced is proportional to the rate of change of magnetic flux linking the circuit. So that is Faraday's second law. It tells us the value or the size of that EMF. Now, what is the mathematical relationship? We use this to denote EMF. So the mathematical relationship is EMF proportional to the rate of change of magnetic flux, right? So this is the mathematical relationship. So if you remove this, we can just say that the EMF is the phi b dt. So this is Faraday's law. Now, if we have, let's say, so many turns, this is a case where we have just one turn of conductor. So if you have so many turns, you wind your wire so many times, 1, 2, 3. So it means you have so many turns. For in that case, we're going to introduce number of turns to that equation. So I would write for n turns, then the EMF becomes n the phi b dt. So this is now Faraday's law, but this law is not yet complete. There's a modification that is made to this, which we'll see just shortly after this. So here n. Now this equation can still be written this way. I can write this as the EMF equals I'll take this number of turns in because it's a constant. So we can always bring it out or take it in. So I can now write like this. N phi b dt. I can write this like this. So that you take note of the fact that number of turns that times flux, the product of number of turns and flux is known as flux linkage. Flux linkage, which I will denote with the symbol psi. So which simply means that I can write this equation as this, the psi, the t. This is Faraday's law. This is Faraday's law, right? Yeah, so you take note of this law. This is incomplete. Now, a modification was made to Faraday's law. The modification was made to include the direction of that EMF so as to obey the law of conservation of energy. So that is why that modification was made to Faraday's law, so that this law can follow the conservation of energy principle. Now, who made the modification to Faraday's law? The scientist is who we know as Lenz. So, and we know this law today as Lenz Law. Lenz Law. Now, what does Lenz Law say? Lenz Law states that the induced EMF is in a direction that opposes the changing flux that produces the EMF. So I'll repeat. Lenz Law states that the induced EMF is in a direction that opposes the changing flux that produces it. That is, let me write it quickly. The induced EMF is in a direction that opposes the changing flux that produces it. So this is what we know as Lenz law, and Lenz law included into Faraday's law would now have a relationship like this. So this is now what we know as the new Faraday's law. EMF equals minus N the phi dt. So this is now Faraday's law, where this negative sign was introduced by Lenz law, and the negative sign gives us the direction of the induced EMF. So it means that the induced EMF would always be opposite to the direction of the flux. So that is Faraday's law, and this principle we're going to see the application of Faraday's law in so many other areas. But quickly, let's look at other forms of Faraday's law that are important to us. Now, if you recall from magnetism, we know that magnetic flux, this is magnetic flux. Magnetic flux is actually BA cos omega t, or you can say cos theta, and theta is omega t. This is magnetic flux. So that if I introduce this into Faraday's law, I can quickly see that the EMF is going to be minus N D. Instead of phi b now, what will I have? I will have BA cos omega t dt. So now what I'm trying to do is I'm going to, this derivative is a derivative with respect to time. So it means I'm differentiating this equation with respect to time. So I would have, when you differentiate cos omega t, this would give us minus omega sine omega t. So I'll quickly write the result. So cos, if you differentiate cos, you get negative sign. So that negative from this cos will change this, it becomes positive. So I have n, these are constants, so you bring them out, nba. Then when you differentiate omega t, you have omega. So I have omega. When you differentiate cos, you have sine. So I have sine, then you write back omega t. So this is what you get when you differentiate this. Now the negative sign is gone because of this derivative. Now, very quickly, you'll see that I can write the EMF as a sinusoidal equation. I can write it as epsilon naught sine omega t. So that when I compare these two equations, you then notice that the peak EMF is now actually equal to this part. So epsilon naught is equal to NBA omega. Epsilon naught is known as maximum EMF. You can still call it peak EMF. You can still call it amplitude EMF or maximum EMF, right? So that is Faraday's law in another form. Now, very quickly, this equation points out a good number of things to us. It tells us the quantity upon which the EMF that is induced would depend on, right? Yes. So it means that one, so let's write this as deductions from Faraday's law. Deductions. So number one deduction is that the induced EMF is dependent on the number of turns. So the induced EMF is proportional to the number of turns. The EMF is proportional to the number of turns. So what it means is that if you want to increase the induced EMF, then you should increase the number of turns, right? You can try this experiment at home. Bring a copper wire, wind it, create like, let's say 20 turns of winding around it, then move your magnet. You'll notice that the strength of the EMF would be different from when you have, let's say, 50 turns. So it means if you want the induced EMF to increase in magnitude, what do? You increase the number of turns. So what it means is that I have 20 turns and I have 50 turns. Which of this number of turns will give me a higher EMF? Of course, 50 turns. So that is what the first deduction is pointing out. Then the second deduction again is that the induced EMF is proportional to the strength of the magnetic field. So it is EMF is proportional is proportional to the strength of the field. So what does it mean? It simply means that if you have two magnets, one is smaller and one is bigger, so which of these two magnets would give you a higher EMF? A bigger magnet, because a bigger magnet would create a stronger field. So it means that the stronger the magnetic field, the higher the EMF that would be induced. So bigger magnets, bar magnets, of course same bar magnet, bigger bar magnets would give you the higher results than smaller bar magnets. So EMF is proportional to the strength of field. So you can see it, B represents the magnetic field strength, right? Yes. Number 3, deduction, you should also take note of, is that the EMF is proportional to the area of the loop. So you have a loop like this now. This, my hand forms a loop, and this is my magnet, right? So if I create a larger loop, then I would have an increased EMF. So the EMF again is proportional to the area, or you can say size of the loop, right? So the bigger the loop, the bigger the EMF. Then fourthly, we can also see that the induced EMF is proportional to the speed of movement of the magnetic field, or it's proportional to the speed of rotation of the magnetic field. So the EMF is proportional to the speed of the field. So if the magnetic field changes very fast, then EMF would be increased. If it changes slowly, as I bring this as my magnet and I move out, I'll get small value. But when I begin to move it fast, the EMF will increase. That is just what this is saying. So these are points that you should note about Faraday's law and induced EMF. So it means that the induced EMF would be dependent on these 4 factors, which is very important for us to note. So very quickly before we continue, we're going to take a problem, maybe say 2 problems under this. I'll clarify this concept to us. So let me put down the questions. All right, so let's look at this first problem that will illustrate Faraday's concept. And we have a 2 cm by 1.5 cm rectangular coil. So it means they've given us parameters to determine the area of the coil, which is rectangular. So first, I have, let's say length is 2 cm. So I have to divide this by 100, which would give me 0.02 meters, right? Then my breadth is 1.5 cm. I will divide this again by 100, which will give me 0.015 meters. This 0.015. What am I writing? 1 to 0.015. So let's manage the space. So that is my breadth. Then they said a rectangular coil has 300 turns. So let's find the area first. So the area is going to be length times breadth, since it is rectangular, which is 0.02 times 0.015. So quickly I will punch that to find my area. So my area is simply going to be 0.02 times this. So my area is 0.0003 meter squared. So that is my area. And the next thing they give us is the number of tons as 300, right? Now rotating in a magnetic field B. They didn't give us the value B. So the magnetic field is B. I believe that's what we're looking for. Magnetic field B at 60 hertz. So the frequency is given to us. Frequency is 60 hertz. Now, what must be the value of B? So that's what we're looking for. So that the EMF generated is 24 volts. So the EMF, which we consider as the peak EMF, is 24 volts. So we want to find this. So very clearly, you can see that you have area, number of tons, EMF, then you have speed. We can get speed since we know frequency. So let's quickly get the angular frequency or angular speed. Omega is 2 pi f, which we know. So omega is going to simply be 2 pi I'm considering as 3.14 times frequency 60. So that we see that our omega is going to be, so let me quickly multiply 120 by 3.14. 3.14. So this would give me 376.8 radian per second, rad per second. So that is our speed. So quickly, we're going to rub this side so we can now find the magnetic field, the strength of the magnetic field. So you recall that peak EMF epsilon naught or E naught is equal to NBA omega. So recall we derived this formula just now. So I'm trying to find B. So if I make B the subject, I would have this over NA omega. So B is going to be this, which is 24. N is 300. Area, we got area as 0.0003. Then omega is 376.8. So let me quickly punch this and see what we have. So we have 376.8 times 0.0003 times 300. So I have 24 divided by 33.912. So if I divide this finally, 24 divided by 33.912, this would give me 0.708 Tesla. So this is what we have as the strength of the magnetic field. So which is very simple. I'll take one more problem, then we'll further this study. So this is it. So do well to take note of these things. All right, let's just move on for now. Let's look at the next concept we want to analyze. So we want to consider what we know as motional EMF. Motional EMF. Now, I want to point out that Faraday's law specifically draws from electromagnetic induction. Electromagnetic induction covers Faraday's idea and motional EMF. Now, what is Faraday's idea? Let me quickly recap so that you can understand the difference then with the motional EMF. Faraday's law talks about EMF being induced whenever there is a changing magnetic field. So if you are moving a magnet and you're changing magnetic field, then you can induce EMF in a conductor. But the idea of motional EMF is generated in a conductor whenever a conductor moves in a stationary magnetic field. When a conductor moves in a stationary magnetic field, the EMF that is induced in this case is what we know as what? Motional EMF. So this is induced or generated when a conductor moves in a stationary okay, let's just say stationary magnet, right? Yes. Now, when we say stationary magnet, of course, you know that flux would change, right? Because if a conductor moves across a stationary magnet, of course, as the conductor cuts the magnetic field, the flux would be changing. So it's still the same idea of electromagnetic induction. So in this case, also, EMF would be what? Induced. And this EMF that is induced by moving a conductor in a fixed magnetic field, that EMF is known as motional EMF. Now, what actually happens here is that, say I have magnetic field like this that is pointing into this board. I have magnetic field pointing into the board. Then I have a conductor. This is a conductor, right? And this conductor, I'm moving it in this direction. This is the direction of motion. I'm dragging it in and out like this. Remember, my magnetic field is into the board, and then my velocity is like this. Your field and velocity are perpendicular, right? Because the field is into the board, the velocity is this way, which is perpendicular. Now, you will notice that there will be a magnetic force on the electrons distributed around this conductor. Remember, every conductor has electron, right? The electrons are charge carriers. So since you have electrons, if you move this conductor in this way, magnetic force will be generated in this conductor, and that magnetic force would act downwards. So let me do it this way. This is FB, magnetic force, so that it is perpendicular to the velocity and the magnetic field. So if you use your Fleming's left hand rule, you can tell that the magnetic force is acting downwards. So the magnetic force acting downwards will drag the electrons, will drag them so that the electrons would concentrate at this end, at the bottom part of this, thereby making the end of this conductor to be negative. Now, relative to this end, this part becomes what? Positively charged. So that there is a potential difference across the ends of this conductor. Since this is positive and this is negative, there is a potential difference, which is what we know as what? The motional EMF, right? Yes. Now, since you now have a potential difference, it automatically tells you that there will be an electric field created, and that electric field would give rise to an electric force which would act opposite to the direction of the magnetic field. So these are electric force, right? At equilibrium, the electric force would equal to the magnetic force. So under equilibrium condition, these two forces, because they are opposite, they will balance each other and remain at equilibrium. So in this case, we can equate this so that we can use this to derive the relationship for the magnitude of the motional EMF under this condition. Now, what is electric force? Electric force is actually Q, the charge, times the electric field, E. What is magnetic force? Magnetic force, since it is perpendicular, magnetic force is QVB. This is magnetic force. So you can clearly see that Q, the charge of the electrons, would fizzle out, and then we have that E is equal to VB. What is V in this case? V is velocity. I'll define these terms. Now, very quickly, if I multiply through this equation, multiply through by L, that is the length of this conductor, which is L, right? And if I multiply through this equation by L, I would have in this case EL equal to what? VBL, right? Yes. Now, if you recall, you'd recall that under electric fields, when we studied electrostatics, we mentioned that EMF or voltage V, or potential difference, this is equal to EL. So you recall that we gave this relationship, or we called this V in that particular video. V equals EL, where V, I'm not using V because I already have V as velocity, so I won't be using V. So you take note that this is what we are using under this as EMF or voltage, so that I can quickly replace this. Since EMF is EL, I can replace this with EMF, and I would have that the EMF becomes VBL. So this equation we have derived, this is the equation for what? Motional EMF. Motional EMF is given as E equals VBL. So in this case, V is velocity. So let me quickly write it here. Let me define those terms so it doesn't confuse us. V is what? Velocity, not voltage. Velocity. B is the field, magnetic field strength. The field strength as magnetic field. Then L is length of conductor, length of this conductor, length of conductor. Then this, of course, is EMF, that is the motional EMF, right? Yeah, so I'll take a problem under this also to clarify this. Then we move to the last part of this video, which is induced electric field. So quickly, let me put down the question. All right, now we have this example to illustrate this with, but this has a little more application. So let's quickly take a look at it. A wire which moves with a speed of this. So the velocity of the motion of that conductor is 4.6 meter per second, is 17 cm long. So the length of that wire L is 17 cm. I would quickly divide this by 100, which would give me 0.17 meter. 1, 2, right? Yes. So it's 17 cm long and has a negligible resistance. The magnitude of the magnetic field is 0.25. So B is 0.25 Tesla. And the resistance of the U-shaped conductor is 25 cm. Now, what actually happens in this case, this is a special case which still draws from what we just explained. There's no much difference. But what happens is that we have a conductor. This conductor is present in a closed path, a U-shaped closed path. This is fixed, this part, so that you form a closed circuit. While this conductor can move, it can move, but this U-shaped is fixed. It doesn't move like this. So, but this conductor can move. So what happens is that since this whole thing forms a closed path, there will be a current that would flow through this U-shaped conductor. So that is what they want us to find, the current. Remember, EMF will be induced in this conductor, which already forms a closed path, and therefore current would now flow because there's a closed loop. So they want us to find the current that will flow through this path, noting that the resistance of this path where the current would flow through is given to us as 25 ohms. So the resistance R is 25 ohms of that U-shaped closed path, right? So that is just what they want us to find. So the same concept is what we are going to use to find that. So let me quickly rub this side. They want us to find the induced EMF, which is this, and then find the current through that U-shaped conductor. Now they told us that the resistance of this part is negligible. So we're only dealing with the resistance of this. Assuming it wasn't negligible, we can then analyze whether it's in series or parallel. But the resistance we are dealing with is just the resistance of this part. So the induced EMF in this case is going to be BVL, right? We can put negative sign. The induced EMF in this part should be negative, but there's no challenge. You don't really need it again. So our EMF is B, which is 0.25. times the velocity, which is 4.6, times the length of this conductor, this length, which is 0.17. So if I solve this, I'll get that my induced EMF is 0.25 times 4.6 times 0.17. So this will give me 0.19, okay, let's say 196 volts. So this is my induced EMF in the conductor. Now, the next thing they want us to get is the current through the U-shaped conductor. The current is going to be the EMF in that circuit, which is E over the resistance of that part, which is R. So what do we have? We have 0.196 divided by the resistance, which is 25. So our current becomes 0.196 divided by 25. So this is approximately 0.0078 amperes. So this is what we have. So they can still ask us further. They can ask you to find the power in the U-shaped part. We can get that knowing that power P is I squared R. So you can find the power in the U-shaped part. So they can ask that under exam conditions. So this is what it is. I believe this concept is clear. And then finally, we want to mention the concept of induced electric field. Induced electric field. Induced electric field. Now, we already established earlier in our studies of electrostatics, we established that, let me write this, induced E field, electric field. Now, we already established that whenever you have charges, of course, current in a conductor, that you would have when the charges are moving, that it would give rise to an electric field. We know that. So we want to quickly point out from Faraday's concept that whenever you have a changing magnetic field, it would always give rise to an induced EMF and induced electric field. So a changing magnetic field will produce an induced electric field. Produce an induced electric field, right? Yes, so this induced electric field, we want to see the relationship for the induced electric field that is produced. Now, but first thing I want you to notice or take note of, I want you to note 2 points for the induced electric field. One point you should note is that the induced electric field is non-conservative. It is non-conservative. It is non-conservative. Right? It's not conservative, right? So meaning it does not do any useful work. So it's non-conservative. Then second point I want you to note also is that, all right, is still talking about this first point, but when we studied electrostatics, the electrostatic field is conservative, while this one is not conservative, right? Yes, this one depends on the magnetic field, while earlier we considered electrostatic field that depends on charge. So these are points you should note. Now quickly, let's look at the relationship for the induced electric field. Now, you would recall that electric force F is QE. Yes, electric force F is QE, so that work done U is going to give rise to QE, that is force. Now, we want to look at a circular conductor that moves in a magnetic field. So we're considering this conductor that induces electric field. to be a circular loop, to be a circular conductor for simplicity. So if our conductor is circular like this, and it's moving through a magnetic field, just like we have analyzed, magnetic field that is into the board. Now, you notice that at every point, the electrons in this conductor will be moving, right? The electrons will be moving, and the electric field, the direction of the electric field can always be gotten by taking a tangent at every point. So this would be the direction of the field at every point in time. Now, the work done in moving an electron from one point to the same point where it is, the distance that will be traveled through that conductor is the length of one loop, which is 2 pi r. So it means that the work done will be the force times the distance traveled by an electron, which is 2 pi r. So this would be the work done in this case. Also, if you recall from electrostatics, work done U is actually Q, charge, times voltage, or EMF. So that if I equate these two quantities, since this is this, I can quickly see that QE times 2 pi r would be equal to Q times EMF, and this would go, so that I can now make my electric field, this is electric field, to become this over 2 pi r. So it means that the formula for the induced electric field is E, which is voltage or EMF, over 2 pi r. So that is a very important relationship. If we still introduce what we already learned from Faraday's law, from Faraday's relationship, we recall that EMF, induced EMF, is actually negative the phi b dt. This is what we know from Faraday's law. So that I can now introduce this into this relationship, or I can still reduce this by saying negative area b dt. I hope you know these are still the same, because you know that phi is actually b. So I brought area out, saying that area is constant. So it means that EMF is still minus a the b dt. So if I introduce this into this formula, I can still have that electric field is going to be 1 over 2 pi r times this, so that the EMF, I can then bring this. I have 1 over 2 pi r times my EMF, which is what now? I'll bring the negative here. Then I have area times the b dt. This would be my electric field. Now, since we have a circular loop, it means I can use the area of that circular loop to be what now? Pi r squared. So I'll have that E is going to be negative pi r squared over 2 pi r dB dt. If this reduce, and finally the electric field can be written as negative r over 2 dB dt. So this can be a relationship for our induced electric field. This can also be a relationship for our induced electric field. This can also be a relationship for our induced electric field. So at this point, I'm going to end the video. So just a quick recap. We introduced this video by explaining the concept of electromagnetic induction. We said that electromagnetic induction is a phenomenon where EMF is induced whenever there is a relative motion between magnetic field and a conductor. That is electromagnetic induction. And we explained that one of the major laws that governs electromagnetic induction is what we know as Faraday's law of electromagnetic induction. We pointed that these are two laws, and then we talked about Lenz Law, which gives the direction of the induced EMF. Then from there we considered the motional EMF. Then we looked at the electric electric field, induced electric field. This is where we're drawing the curtain. In my next video, I'll be solving more problems under this, and then we'll then further by looking into the applications of electromagnetic induction. We'll notice electromagnetic induction can be applied to electric machines. So we're going to consider electric machines, where we're also going to study the transformers. So do well to stick with me. If you are yet to subscribe, do well to subscribe so that in the next video you'll be updated when I will post it. Thanks for watching this video. This is Prime Concept. Share this video to 10 persons. Tell them this is Prime Concept. Thank you.